Swayam Prabha. Digital India. Educated India.
Again to the new lecture of Fundamentals and Applications of Dielectric Ceramics. So, we will just briefly recap what we did in the last lecture. So, in the last lecture we looked at the concepts related to Bravais lattices, 14 Bravais lattices basically, which is a combination of primitive and non-primitive lattice all the of 7 crystal systems, and then we looked at briefly what planes and directions are in the crystals, which are basically follow Miller indices convention, and then we just introduced what kind of bondings we have, and as it happens in dielectric ceramics, most of the ceramics are ionically bonded materials. Partially they could be covalent in certain cases, but by and large they are predominantly ionic in character, and this ionic bonding provides them strong bonds. As a result, they are very strong materials. They have low coefficient thermal expansion, they have high melting points generally, but they are also brittle, and it is also because of the same reason they also have low electrical and thermal conductivity, and that is why they are dielectrics. And then we have we looked at packing of atoms, because in solids quite important role in determining the structures of these materials. So, we looked at packing methods which can lead to simple cubic structures, body centered cubic structures, then we looked at hexagonal closed packed structures, and then we looked at cubic closed packed structure, considering that all the atoms are spherical in nature. So, these are not closed packed but loosely packed structures, but these packing sequences are possible and they are observed in some solids, and these are basically closed packed. Okay. So, the packing ratio increases as you go from simple cubic to body centered cubic to hexagonal cubic closed pack, but assuming that they are all same atoms, monatomic crystals. If you have non-monatomic crystals, then the packing density will change depending upon the size of atoms. So, in the ABC kind of packing sequence, as we have drawn on the left, can be best described in terms of symmetry by a face centered cubic structure. So, crystallographically speaking, the cubic closed packing structure is also called as face centered cubic structure. So, although here we have shown these atoms a little bit far from each other, in reality they are touching with respect to each other, and this is basically FCC or CCP structure, where atoms are placed at 0 0 0 kind of positions and half of 0. Half of 0 will basically mean you have half of 0, 0 half half, and half 0 half. So, there is so you have atoms, 8 atoms at the corners, which means 1 by 8 into 8. You have face centers, 6 atoms, which means 1 by 2 into 6, because each face is shared by 2 unit cells and each corner is shared by 8 unit cells, and this will give rise to total of 4 atoms per unit cell. ABC kind of packing gives you a different structure. It is called as hexagonal closed packed structure. So, this is the bottom layer, which is the A site, and this is the light blue color is the B site atoms, and then you have A site again on top. So, this is how AB stacking takes place, and in one unit cell, which is this one unit cell here, the one drawn in the red, so in this case the atoms are located at so this will be the one. So, atoms are located at 0 0 0. So, these are 0 0 0 kind of positions, and then you have another atom sitting here, which is 2 by 3, 1 by 3 and half, not 0, but it is 2 by 3, 1 by 3 half locations. So, one is sitting at this. So, this is basically so all these atoms, corner atoms, can be depicted at 0 0 0, and the one in the center can be depicted as 2 by 3, 1 by 3 and half, or you can also write it as 1 by 3, 2 by 3 half, depending upon how you look at the unit cell, but both of them are identical sort of situations. Okay. So, these are the two structures that you come along that you find when you have close packed structures, and this packing factor if you have monatomic crystal is about 0.74, and this can be found out easily by looking at the volume of atoms, all the atoms in one unit cell divided by the volume of the unit cell, and you will easily find the packing factor, which is a trivial exercise. Now, since you can see that all of these structures, they do not fill the space completely. Simple cubic has a lot of gaps in it, body centered cubic has a lot of gaps in it, face centered cubic crystals have a lot of gaps in it, which means you have holes in them. And what are these holes useful for? These holes are called as voids or interstices. They are useful because often they contain impurities. There are smaller impurities such as carbon and iron, they can go and sit in there. And this is useful because carbon and iron is the one which provides strength to iron, otherwise iron will be very weak. So these interstices are something, and these interstices are even more important in case of oxides, in case of dielectric materials, because in dielectric materials what happens is that dielectric material is a combination of cations and anions which are ionically bonded. Generally speaking, anions are bigger as compared to cations. So what happens is that anions generally form the base lattice and the cations sit in the interstices which are present in these base structures, and that is why the concept of interstices is very important, and you need to understand what these interstices are. So in a close packed structure, if you put a layer of atoms like this, so there is this is the bottom layer, let us say A, and this is B at the top. Okay. So you can see that depending upon how the layers are formed. So in the configuration that I have shown here, if you look at, for example, this, so the first layer is covering the, so this is like you can do this experiment at home. You take several marbles, okay, you put the marbles on a plane, just fill it completely, and then take another layer of marbles, put on top of the first layer of marbles. So what you will see is that for example, if you pick one marble in the top layer, the marble in the top layer will sit on a vacant space which is lying at a lower position than the top surface of the atoms in the bottom layer. Let us say this was the point 1 that we described earlier. Okay. So on this point, so this vacant space between the 3 atoms in the bottom layer and the 1 atom which is resting on top above these 3 atoms is called as, so you can see that this point here is coordinated by the atom A here, as I cannot write A, maybe I can write small 1, so Roman letters 1, 2, 3 and 4 on the top. So these 4 atoms surround this little void in the center of this polyhedron that I have formed. This polyhedra is called as a tetrahedra, and this void which is present in this is called as tetrahedral void because it is surrounded by 4 atoms. So this is a tetrahedral void which has 4 coordination, which has 4-fold coordination or 4 atoms surrounding it. And of course you can make a small atom sit inside it, and you can easily calculate using the geometry of tetrahedra that the size of this atom will be 0.225 of the host atom. So if R is the radius of host atom, then the maximum size you can accommodate inside this hole or void without displacing the host atoms will be 0.225 R. So if you have an atom of radius, let us say 0.3 R, which means you will have to displace the host atoms a little bit. Okay. Then you can in the same structure you form another void as well. So if you look at this configuration now, here you have let us say P Q R, okay, and the second layer we have P prime, Q prime and R prime. They also form a void here. So the void between these is located here, and this void has now 6 neighbors, and the polyhedra which is formed by connecting the centers of all these atoms is called as octahedra, and the void is called as octahedral void. Octahedral void basically means it has 6 neighbors, and Octahedra will mean it has 8 faces. Okay. So basically it's an octahedra shaped polygon. It has 8 faces, and again you can calculate the size of the atom that will sit inside this octahedra easily using geometry, and this size will turn out to be 0.414 of the radius of host atom. So minimum size that you can put in there, the maximum size you can put in there without displacing the host atom is 0.414 of the radius of host atom. And these can be easily visualized in a especially in a cubic close packed structure. So let us see how you can visualize them in the cubic close packed structure. So this is the unit cell that I am going to draw. For the sake of clarity, I will not make that atoms touch each other. I will rather draw atoms which are little away from each other. So this is first atom, second atom, third atom, fourth atom, fifth atom, and then I will place atoms at the Okay, so this is a face centered cubic unit cell. Now in this, the octahedral voids are located at positions which are marked by these X's. Okay, and there will be one at the body center. So the easy one is, I can draw one octahedra for the sake of illustration. So if I connect this atom with atom here, atom with here, the atom here, and the atom here. Okay, and if I connect the dots with respect to this, that, and so this is the body which is called as octahedral void. So octahedral voids in FCC structure, they are located at half 0 0 locations, which means edge centers, and one at half of half. So there are 12 edges, so 12 into half 0 0 kind of locations, and 1 into, so there are total of, but each edge is shared by 4 unit cells. So as a result there are 4 octahedral voids in total, considering sharing. Okay. All right. Now how to draw the tetrahedra? Tetrahedra is again very simple. Tetrahedra is basically formed by atoms. So if I connect this atom, if I connect this atom, and if I connect this atom and I put all of them together, then I form a body which is called as tetrahedra. So let me just use a different color maybe. I can use a green color. So this is the tetrahedra that we form, and this atom which sits inside the tetrahedra will be tetrahedral void. So tetrahedral voids in a FCC structure are located at quarter type of positions. So you can have quarter, you can have 3 4 3 1 by 4 1 by 4 and various combinations. So you will have basically 8 tetrahedral voids. Okay. And so you can see that in the previous slide we saw that maximum size of the atom that can be put inside these octahedral and tetrahedral voids is, in octahedra it's 0.414 R, tetrahedra it's 0.225 R. This is the maximum size that you can put inside them without displacing the atoms, and this is very easily this can be very easily calculated. So, for example, for a octahedra it is very easy. For a octahedra, this is the size that you are putting in there. So, basically if all the atoms are touching each other, then you can say that 2 of Ri plus 2 of small r is equal to A, okay. And what is A in terms of r? Because atoms are touching each other, A square root 2 is equal to 4r, and if you just substitute this, you will find r octahedra to be equal to, so this is, let us say, r oct, okay. This will be equal to 0.414 r, and similarly you can also find out what is the tetrahedral size. So, as a home exercise, your job is to now work out what will be the locations in HCP and BCC structure. This is your homework, okay. And also you can calculate the size of atoms which are present in there. Okay, so now having done this interstices thing, let us just go to some of the examples of covalent solids, because now we are moving towards dielectric structures. So, we just look at some of the examples of covalent solids. So, the primary examples of, so although there are a lot of, basically you can say there are group 4 elements such as silicon, carbon, which are covalently bonded. Then we have also group 7b, 6b and 5 elements which are also covalently bonded. So, 7b will be basically halogens, okay. 6b will be basically, you can say H2O, or you can say sulfur S8 molecule, and group 5 will mean you have phosphorus, arsenic or bismuth, etc. They are all covalently bonded. But the most famous example of covalently solids are these group 4 elements, silicon, carbon, etc. And then we have mixtures which also form covalently bonded and which are basically compounds, and these mixtures could be silicon carbide, which is a 4,4 compound. You can also have aluminum phosphide, aluminum arsenide and indium arsenide, which is also 3,5 compound. You have zinc oxide, zinc sulfide, which is 2,6 compound. Zinc oxide is a dielectric material, and we will see what its structure is, and so on and so forth. There are multiple examples of these covalent solids. Oops, I think I had it written anyway. So, basically in these the covalent bonding is because of hybridization of orbitals. So, if you combine 2s orbital with the 2p orbital, you will have 2 sp hybridized orbitals, and as a result you will have different kind of hybridization that will occur. So, if you look at the hybridization schemes in covalent solids, so if you bring in s orbital, so s orbital is spherical in nature, this is s orbital, okay, and then you bring in what we call as, let us say, px orbital. So, if this is x axis, this is y, this is z, then let us say this is your px, okay, and if you and in px you can have py as well. So, if you have along this axis, you will have py. So, this is y, this is z, this is x. So, this is py, and you will also have pz. So, you will have, they are not spherical in nature, they have sort of this kind of shape. So, this is pz, and if you make them hybridize, so now let us go to process of hybridization. Hybridization normally leads to formation of structures which are little asymmetric in shape. So you can have formation of sp3 hybridization. So sp3 hybridization will generally lead to sort of tetrahedral kind of shapes. So in this case, what we will have is we will have scheme something like this. So this is sp3 hybridization that we will have. So we will have sp3 hybridization along one direction, second direction, and the third direction. Eventually, so if you consider all the three directions, okay. So this is for one direction, okay, one of the p orbitals, okay. And if you consider all the three orbitals, then the shapes that you will form is basically something like this. So inside this, so you will have one like this, another like this, another like this, and another like this. So this is how you will have sp3 hybridization that will occur inside these materials. So this is sp3 along this, sp3 along this, and sp3 along that. So this is how you will have all the sp3 hybridization, and this hybridization also leads to angle that you will get 109.5 degrees that you get in these solids. So hybridization can be various types. So what we have drawn is sp3 hybridization, which is basically tetrahedral kind of configuration, but in reality you can also have sp hybridization, which is a linear hybridization scheme. There is a possibility of sp2 hybridization, which is trigonal sort of planar. sp3 what I have drawn is here, and you have possibility of sp3d, you can have sp3d2 as well, okay. These are the possibilities. So in the linear case you will have this kind of hybridization. In the planar case you will have this kind of hybridization. So this is the planar one. This, so sp3 happens in case of, for example, diamond, and sp2 will happen in case of things like graphite, okay. Graphite is sp2 bonded, and carbon diamond is sp3 bonded. So now if you look at the structure of these materials, we have these covalently bonded solids in diamond. So in case of diamond, because of sp3 hybridization, each carbon atoms has and it's covalently bonded, it has 4 neighbors. So as a result, it's tetrahedrally bonded. So what we have is basically carbon making a FCC lattice, and 4 carbon atoms are tetrahedrally bonded, sp3 hybridized to these atoms. So the way it happens is that each carbon atom, whether you look at this atom, whether you look at face centered atom, or whether you look at the one which is sitting inside the tetrahedra, all of them are tetrahedrally coordinated, okay. So in some sense you can say, so if you look at the top view is like this. This is the unit cell, this is the base unit cell 0 1 0 1 0 1 0 1, these are the corner atoms. So this is, you can see x y, so this is x, this is y, and the z is perpendicular to the plane, right. So z x y position is obvious, z position is written, all right. So you can see that these are all, so these are the atoms at face centers, these are corner atoms, these are the ones which are tetrahedrally coordinated. Atoms. So you can see that this atom will, sitting here, will coordinate with, it will coordinate with one of the atom. So if you look at, so this is what is this atom, it is coordinating with, so if we have drawn this tetrahedra, it is coordinating with one of this atom, one of the face centered atoms on the other side, one of the face centered on this side, and one of the face centered atom on this side. So, it is coordinating with these 4 atoms. Now, crystallographically speaking, even these atoms which are sitting here, they are also coordinated. So, instead of drawing the lattice corner here, suppose if I draw the lattice corner here, if I draw the lattice corner here, then if I convert this, if I take 1 by 4 position as 0 position, then this will become 0 and 1. This will become half. There will be identical atoms sitting here, this will be at 0, 1. What will this convert to? This will convert to tetrahedral position, that is 1 by 4 position. This is at half, this will convert to 3 by 4 position. So, basically all the atoms are tetrahedrally coordinated, whether you look at the one that is sitting on face center or the corner, or whether you look at the one which is sitting at the tetrahedral void. So, essentially it is a diamond cubic structure is basically a combination of 2 FCC lattices of carbon, one shifted by 1 by 4, 1 by 4, 1 by 4 with respect to other. Okay. So, you have 2 cubes, the second cube is shifted with respect to the first one by 1 by 4, 1 by 4, 1 by 4. And you can see that since carbon makes FCC lattice, theoretically speaking there are 8 tetrahedral voids, but only 4 of them are occupied. You cannot make 8 of them occupied. If you make 8 of them occupied, the problem is one carbon atom will have 4 neighbors, but the second one will have 8 neighbors, and that will violate the bonding. So, as a result you will have only 4 tetrahedral voids filled, not 8. So, this is diamond structure. You can have graphite in which carbon is bonded by these 3 atoms, sp2 hybridized. So, this is covalent bonding within the layer, but between these we have secondary bonding, and that is why carbon is very hard because of its directional nature. It is very hard, but graphite is loose. It's a layered material. It's used as a lubricant in many cases. So, this is what we have in terms of diamond. Because of its sp3 hybridization, a strongly directional covalent bonding, diamond is a very hard material. So, other materials also form this kind of structure. So, if you replace this carbon sitting in a tetrahedral void by, let us say, sulfur, and carbon by zinc, or zinc by carbon, you can this could be zinc as well, then this makes a zinc sulfide, or similarly you can have silicon carbide. So, silicon carbide and zinc sulfide also make this structure. So, there is a 1 FCC lattice of silicon and second FCC lattice of carbon. So, this second FCC lattice of carbon is shifted by 1 by 4, 1 by 4, 1 by 4 with respect to the first lattice of silicon, and same is true for zinc sulfide. So, these are the forms of carbon that are covalently bonded forms of carbon, and one final one is the C60 structure, which is basically a truncated icosahedra. Icosahedron is a polyhedra drawn here, and C60 is basically if you truncate the corners. So, some of the corners will appear as, since some of the corners have 5-fold rotation, other corners have 6-fold rotation. So, you will see a series, you will see arrangement of pentagons and hexagons. It is like a buckyball, a football shaped structure. This is a C60 structure. So, we will stop here today. What we have discussed is structure of these covalently bonded solids, which are primarily decided by bonding because of directionality in the bonding and hybridization that is required. The dielectric ceramics on the other hand is typically ionically bonded predominantly, and which is based primarily on filling of ions, and so we need to understand that how do they form in the next lecture. So, we will stop here. Thank you very much.